Welcome to the section 1.7 pre-class video assignment. So in this section, we are looking at using special substitutions to solve certain types of DEs. So there's a couple of classes of DEs that we can solve here. So in this video assignment, we're really just going to look at the two classes and be able to identify them, and we will talk about the method in class together. So there's two types here. The first one is something called homogeneous differential equations. This is slightly unfortunate. I believe we've used the term homogeneous previously in the course. Usually homogeneous is simply a DE where it is set equal to 0. This is a different use of the term, and probably the less important use of the term here. So this is the term that is used. Again, it is a bit of a duplication in terms. The other term, the other use of the term homogeneous is actually probably the more important one. But in this section, when we say homogeneous, we mean the following. So a DE, a differential equation, and first order differential equation of in normal form, dy dx equals f of xy, is called homogeneous if the function on the right-hand side, the f of xy function, behaves this way. That is, if you replace x by tx and y by ty, and simplify, you end up basically back where you started with a function f of xy. So this is the idea of homogeneous, again, just for this section only. So we want to, in order to use the homogeneous method of substitution that we're going to see in this section, we need to be able to recognize these things. So that's really our first exercise here, is when do we have a homogeneous? So a couple of examples here. Here is a DE. First order, we can see our f of xy function on the right-hand side is 2x squared plus 3y squared. So this is basically the test for homogeneous. If we plug in tx for x and ty for y, let's see what happens. So if I substitute that into this function f of xy, we get this. If we simplify and try and work at it at all, we can certainly write tx all squared as t squared x squared. Similarly, we get t squared y squared. There's a common t squared there, which can be factored out. But I end up here with a expression t squared times the original function f of xy. This is not homogeneous, right? This is not getting us back to f of xy. So this one here is not homogeneous, and then the method we're going to learn of this section would not apply to this one. All right, here's another example. What if we had something like this? Notice this function is dy dt. That's slightly unfortunate. Again, this means the name of the function is y, the independent variable is called t. Now, since I've already used the letter t for the independent variable, I better use a different letter when testing, because it's not the same t necessarily. So I chose to use the letter u for this example. So if I put in ut for t and uy for y, this would be my test to see if we have homogeneity here. Again, I'm looking to see if this ends up being the same as the function f of ty. So if we do this, substitute in, we get this guy here. So you could again see this ut all squared, uy all cubed, ut all cubed, uy all cubed. So clean it up a little bit. This is a u squared t squared times a uy. So there's a u cubed t squared y. There, over here, we have a 3 u cubed y cubed. We have a u cubed t cubed, and we have a plus u cubed y cubed. So if we notice here, as you can see there in the notes, there is a common factor of y cubed everywhere. The y cubes therefore can cancel out, and once you cancel those out, we are back to f of ty again. So this one is homogeneous. And there are exceptions, but this is sort of fairly typical. You can kind of see why this one was homogeneous, because with this quotient here, we had a chance of canceling out our u's. In the first example, there was no way we were going to cancel out the t's because there was nothing in the denominator that we had to work with. So this is the idea of homogeneous. We should be able to check it like this and see if it works. So here's a little exercise on MyOpenMath to try that. Okay, then the other type of problem we're going to look at is something called a Bernoulli equation. So I'm going to move down here to the Bernoulli section. So just a little section here. This is a Bernoulli or Bernoulli. I was always taught to call this Bernoulli, but again, other people call it Bernoulli. Anyway, a Bernoulli is one that looks like this. You can kind of think of this as being an almost linear equation. This looks a lot like a linear equation in standard form, except that it's got this y to the power of n over here on the right-hand side of the equation. In a linear equation, that's not there. If that were not there, we would have a linear equation. So when we have this y to the n here, this is a Bernoulli equation. So this works for actually any power n. Often when we write n, it means we intend it to be an integer only. That is actually not the case here either. This can be any real number. The only thing we are accepting here is that the y should not be here. This is not to the power of 0. Well, that's fairly obvious. If we have y to the power of 0, y to the power of 0 is 1, and then that is not something different. That is just a linear equation. So that is not addressed here. We don't need a new method to solve something like that. We also don't care about n equals 1 either, because if n equals 1, this is of course just a y. And if this were just a y, we would simply move it to the other side of the equation, factor out the y, and that would just change the form of this linear equation. We'd have a dy dx plus, and then we'd have a function of x, which would be p of x minus f of x times y equals 0 on the other side. So neither 0 nor 1 are valid here, in that they don't, if n is 0 or n is 1, this can still be considered just a linear equation, and we don't need a new method for it. So it does not have to be 0 and 1 doesn't matter. We don't care about those, but it can be any other real number. So it can be a fractional exponent and so on here for this method. So that's really all we want to be able to do, is to recognize this is a Bernoulli equation if we have y to some power here, and that power is not 0 and not 1. In this case, again, there is a special substitution that basically allows us to solve this. So give that a go. There's a little question here to test you on identifying these Bernoulli equations, so give that a go. All right, so what remains then here is just going back briefly, some prerequisite questions here, but just briefly, in both cases, actually, but just let me go back to the beginning here. When we're working with one of these homogeneous DEs, there is a special substitution that turns a homogeneous differential equation into something that is guaranteed to be a separable differential equation. You don't need to worry about how that works for now, but that's what's going to happen, and we will cover that in class. But the point is, in order to solve a homogeneous equation, we make a substitution that turns it into something that is separable. Once you have something that is separable, we know how to solve those. So what you'll find here is there are some examples like this one in our notes, and again, we will go cover this together in class. This is a separable DE, and we can separate it. So it is good practice here. We're going to have you practice on solving separable DE. So give this next question a go. Again, then, and another thing that's going to come up here, as you can see here, is that in some of our examples here, it's not uncommon to run into a partial fraction decomposition to perform. So that is something you're going to review again here on My Open Math. And then last but not least, we have a similar situation in the big picture here when we solve Bernoulli equations. There is going to be a special substitution that we make. When we make this special substitution into a Bernoulli equation, it turns it into something that is linear. So again, we will end up needing to be able to solve linear equations. So we did work on those, but again, you shall practice that here. I have a little example or two to practice on. All right, so again, the main topic so far for the pre-video assignment the pre-class video assignment is to just familiarize yourself with the definition of homogeneous and testing whether something is homogeneous or not, and being able to recognize whether a DE is a Bernoulli equation or not. We will work through the rest of these examples together in class. So that will be it for this video assignment. Thank you.